Thank you, Carol. Um, what I'm going to talk about today is some of the towers that we have designed and gone through the process to different levels of design. Uh, Several of these are not built and probably will not be built during my lifetime, but they introduce ideas for how to design super tall buildings and how to go taller than the typical buildings that you see that are being constructed these days that are super tall buildings. Many of these explore forms and provoke research into what a super tall is, and to some extent, a direction towards a new category of that we call megatall. And for me, that word megatall means a cluster of buildings, not just one building, but connecting buildings and going to a new typology of tower than a single tower. And how tall can you go for a single tower? So I'll show you a couple of examples of that at the end, and then I'll get to another question, which is how tall can we go? And the real answer to that is we don't know, because we don't know what we don't know. We don't know aspects of how height is going to impact the livability of spaces when you get above a certain height. We do know, and I'll talk about that at the very end. But the other thing I wanted to mention is that much of this presentation that I'll be showing you is compiled in a book that we are publishing and should be out in electronic form within the next couple of weeks, called Supertall, Megatall, How High Can You Go? And it's basically a compilation of all of the high-rise and supertall and megatall buildings that we have done during the years between 2006 and currently at Adrian Smith plus Gordon Gill Architecture. It's a 590-page document, so it really gets to a lot of detail on each of the towers that we have studied and designed during that 15-year period. So with that, let's start. So this happens to be the cover to the new book, Supertall, Megatall, How High Can You Go? And it features a very early design direction for our project in Wuhan, China, that was to be 636 meters tall. And initially the idea was to integrate wind turbines into the corners of the building to generate some power for the use of the building. And you'll see that theme throughout several of the buildings that I'm going to show. So the first chapter is really innovative systems, and it has a lot to do with structural integration, informing the configuration of the design itself. And I chose this one out of 5 or 6 buildings that are in this chapter. I chose One Park Avenue, which is a design that we did for Dubai in 2008. And our structural engineer was Halverson of Halverson and Partners. And the MEP engineer was Siska Hennessy Group Inc. And this building, I love the form of this building, and we discovered the structural identity for this building from a 15th century study by a mathematician and how to connect the weaving fabric of this together. We started that as a starting point, but because it's in Dubai, we wanted to have a relationship with the Gulf, because ideally this building was initially designed for an island in the Gulf. So the fluidity of water became a driving force for it, as well as the historic aspect of the pearl fishing industry that Dubai started out its foundations on. So you can see the building here is a very evocative form, which has the woven structural element as the framework, and then the infill with soft curvilinear elements that started out as trying to identify with the pearl. And so what you see here is a very familiar now structural idea of the center core with a triangular relationship and mega columns around that core. What you're seeing here is a design that had round columns on the corners of each of the three legs that this building had. The building design were a series of sloped and curved walls that went up through the tower like the ribbons and like these drawings illustrate. I mentioned the 15th century image is shown here on the left of the screen, and then attempts to integrate pearls that look more like eggs here on the next two images. And then as we move from left to right is the evolution of the early design to get to where we currently are. This project went through schematic design and into design development, all in 2008. And then the crash of 2008 hit, and everything stopped worldwide, basically for a period of time as it related to supertalls and development in general, and especially in places like Dubai. So this one was first put on hold and then has never picked up. But part of the aspect of designing this tower was to integrate sustainable features into it to see what we could do to generate power for the building itself. And height has one significant aspect to it that low buildings don't have, and that is wind, and how wind affects the design of the building, but also how we can use wind speeds as they get nearer and nearer to the top to generate power for the building through turbine integration, as seen in the diagrams. Wind also has a strong impact on the forming of the design, as you will find out in future lectures by Bill Baker and others. The design of the building of a supertall is uniquely different than the design of something in the 60-story range or less. And that unique difference is the impact of vortices on the tower and how those vortex actions can create flutter movement within the tower, that the kind of movement that you see in chandeliers moving, or you see in toilet water, the water in your toilets shaking a little bit and rippling. That's from the acceleration of movement that's created by wind that's trying to get around the building and then trying to get into the void space behind the building. And the action of that is actually a sideways force, a pull and push force that causes, that can cause flutter in super tall buildings, not to mention megatall buildings that. So much of the wind tunnel activity here is determining not only the overturning moment or the torsional movements of the building, but also the fluttering that's created by the vortex action. And this study, this aspect to research and development and wind interaction with super tall buildings is a relatively recent phenomena that has been discovered first by buildings moving too much, and then by wind tunnels that can help measure the movement of the buildings and the flutter, and actually the wind tunnel is responsible now for assisting engineers and architects in the site planning of the buildings and the orientation of the buildings as it relates to the prevailing strong winds that are going to affect the building on a yearly basis. So this is what a wind tunnel test looks like. And these buildings in the wind tunnels always have a series of points within them that are used to measure the wind at those different points. And that information is gathered with sensors that then compile the data and give back to the engineers for study and investigation on fine-tuning generally an overview of the structure, but then fine-tuning the structure on a ongoing basis. Things like the Burj Khalifa went through multiple wind tunnel tests, first with the overall, the general, then more specific, and it affected the orientation a little bit. It affected where the steps were on a couple of the legs, and it ultimately fine-tuned the spire component of that building as well, as Bill Baker in the next discussion will talk about, I'm sure. So another aspect to the tops of these buildings that we're starting to look at now, really initiated from this building, the Park Avenue Tower, as what can we do at the top of the building that is significant and memorable. And to date, most tops have had a sort of one-story level that that's dedicated to the observation deck, and it doesn't go beyond that. But we've found now that the observation experience can be a strong financial generator for the development and for the developers themselves. Burj Khalifa generates anywhere between 150 and 250 million dollars a year just on their observation deck, whether that's gross or net. So there's a great desire to have people go to the top and to look around the top and experience that height in buildings, but there's also the opportunity to make that a wonderful event experience in and of itself. So we started researching that in this building. This building also talks about the interaction between the facade and the interior space. And in this building, the skin of this building was laced with light shelves and shading devices that both reduce the amount of natural light that's coming in directly into the tower, into the occupiable spaces, but in areas where it was facing sun in Dubai, we were using photovoltaic cells to gather energy from those cells to help minimize the energy effort in the building, energy effect in the building. We also were doing that from the point of view of the interior tenant space by minimizing the light, the artificial light we would have to use by doing parabolic reflectors in every bay of the building. And that also helped to reduce the amount of energy to the building. This diagram basically goes through a whole series of elements that we look at on every building now in terms of how we can reduce energy in the design of the building itself, in the use of materials, and also the method of generating power in the building, whether it's geothermal, wind, solar, hydraulic, hydronic, etc. So we graph this periodically. And this is showing the early structural concepts for the building. And the basic form of the building as it steps up. The fact that we go from a larger floor plate to a smaller floor plate is part of the engineering aspect of trying to reduce and mitigate the vortex shedding of the tower, and making floors different along the way helps to do that, and also tapering the tower helps to do that. So many of the towers that you see in Carol's show will be shaped towers that reduce the size of those floor plates as they go up. Not all, but most. This gets into the second chapter, which is harnessing energy and the integration of solar and wind power, as I've talked about on that particular project, we think is important to do typically. But in the photograph near the center, upper center, you'll see the Pearl River Tower, which I worked on. I was the design partner on at Skidmore and Merrill in 2007, just before Gordon and I left to do a new firm. And what you see there is the shape of the tower is directly related to the wind direction in Guangzhou. And it's attempting, actually quite successfully, to take the wind that hits the building and to funnel it into the four openings that you see on the facade. Those four openings are at the mechanical levels, but the facades are dipping down from above and up from below to help, and also in a slightly concave facade to move the wind through those four openings. And what's happening in those four openings are wind turbines that wind is driving. So we're using the shape of the building to actually affect the performance of the building. And an offshoot to that idea was that as the wind is moving through those openings, it is affecting the vortex action on the back of the building. It's like a series of wind accelerators. As the wind gets to that point and moves them through that building fast, that wind is like blowing at a ribbon of air, and it's disrupting that air movement. And so it actually is another way to effectively work on the vortex method, to mediate the vortex forces. So when we started the firm, we had no work. What do? We wanted to take that idea of wind turbine action and for being shaped by the wind and look at it in other manners, because what became apparent during the study of that was that the wind forces are naturally the strongest on the corners of the building, because the wind is trying to get around the building and it has to get around the corner to get around the building. So why not try to capture the speed of that wind within the corners? And perhaps that's the best place to integrate wind turbines into a building, is where this wind is naturally speeding up. So we call this building Clean Tech Tower, because what we were trying to do here is something approaching a zero energy building as well. And you can see the image here is an 80-story building in Chicago on an available site that's still available today. But we also, you can see how we've looked at not only the sides or the corners of the building, but also the top of the building, because the wind is also trying to move up and over the building itself. So we've shaped that top and layered it with a level of glass material that acts as a compressor. And we use that compressor language both on the top and on the corners of the building. So it captures the wind and helps drive it into and through the oculus or the openings of the building to drive the turbines that are on the corner. And this also shows how at the base of the building, the turbines which are in the pinch points start out with larger sections of facade, and then as it gets near the top, they get closer and closer together, and that's because the wind speeds are higher up above than they are below, and so you need less surface to drive the wind into the pinch points to drive the turbines. So that's how wind is shaping this building. And those are what the oculus look like when the turbine is there. And we also look at the impact of sun on the building, not just from collecting sun power through photovoltaics, but in this case, looking at the sun as a thermos bottle, or the building as a thermos bottle, and how the sun is impacting the air that's trapped between the outer layer and the inner layer, which we call a double wall now. But an interesting thing happens is that the sun is heating up basically the south facade. In the afternoon, it's facing, it's doing the west, and in the morning, it's doing the east. But in the south facade is when it gets the hottest, and the molecules are heating up in the air cavity. And if we can find a way of just moving that air within the air cavity from the south to the north, we can heat up the air around the north to be roughly the same temperature as the south. And we've done studies where, in fact, I've experienced it, where in a cool day in Chicago of 30 degrees, you can be on the south side of the building in one of these double cavities if it's 3 to 5 feet deep. And you'll experience the temperatures on the south side of the building could be 80 to 90 degrees in that cavity. But on the north side, when you walk around it to the north, it's going to be at 30 degrees or maybe 35 degrees. And if you can move that 80-degree temperature into the 30-degree temperature, you can create an envelope of 50 degrees for the entire building. So your air conditioning and heating, in this case, the heating is, you're only heating from 50 to 70 degree temperatures on the interior surfaces or interior occupied space, which is a big difference between 20-degree differential and a 50, 60, 70, 80-degree differential that would happen without the double wall. The next chapter is really designing an icon. Super tall icons as catalysts for development is one of the topics that we frequently hear about and talk about. And where that was first exhibited was on the Burj Khalifa, which you see in the inset photographs there. The developer named Emaar had purchased 300 acres around this site, and their intent was to do very dense development of buildings in the 30 to 40-story range. And in order to do that and to generate interest in those sites, they felt that to do a super tall tower on that site, in the middle of that site or someplace close to the middle, would create the center of gravity, so to speak, for that site to identify with. So we designed that tower to be the world's tallest building. I was at SOM at the time. We worked with Bill Baker and many others on that, and we developed Burj Khalifa to be the tallest building in the world, and the steps that it contains were part of all the investigations that we just talked about in terms of vortex shedding. And they were partially informed by the wind tunnel analysis. So moving to the new firm, we get a commission, we get into a competition for commission to do the next world's tallest building in Jeddah, Saudi Arabia, for Prince Al-Walid and the KEC company that he heads there. We win the competition, and so we start to design the competition, the building. This is part of the competition process. And what we identified the building with, the the story behind the building here was to identify with Saudi Arabia as a country that wants to become one of the great countries in the world and one of the power brokers in the world. So the strength of that that intent is part of our investigation, but it's about growth and development of the country to get to that point. And so we looked at desert grasses, we looked at palms and the configuration of palms, and certainly before they even emerge as spreading out, there's a point to the palms, and you see certain pieces of the palm as leaf forms that really started. So we developed the concept and the form based on that idea of new growth and development into a significant whole. And this shows you basically the completed model of the tower, which has the three sides. And this is an evolution. I always describe this as an evolution from our work on Burj Khalifa. And in the sense that it's three legs, it has a center core, it has shear walls that are on 30-foot centers that march out to the point. And but the growth of the idea here, I think, is that in the tapered form that we have here, the tapering is probably the most efficient way for mitigating the vortex actions on buildings. If the taper is significant, and the taper is significant here. We understand that the taper of this building is slightly more efficient than the stepping of the towers. And it also relieves the contractor from having to transfer any loads that might be caused by a setback of 30 feet or so, so that you're never transferring the energy. You're always bringing the energy down through the structural elements, and that corner is just moving in as it goes up. So it's affecting the end units, not the whole building. And then we talk about why do you go tall? And if you look at the drawing on the lower left of this, you'll see the red marker is Kingdom Tower, which is now called Jeddah Tower, but you'll see the area around it all being developed as individual sites. And that was very much the rationale for having this as a new world's tallest building. And I can tell you from many instances of clients attempting to do a world's tallest building, it's always their first thought is that world's tallest buildings, when they start out, they always get publicity. They're always in every magazine and every newspaper in the world, basically, as Dubai starts the world's tallest building, or Saudi Arabia is doing the new world's tallest building, and it creates a buzz about the building. So that's one reason why the world's tallest building becomes an anchor to these developments now, that they know that that is what it can generate in terms of identity to a district and a place. Other reasons for doing it, there is ego involved in it, and some developers will go for a world's tallest building because they want to be known as owning the world's tallest building or having the world's tallest building. But there are also national tendencies for world's tallest buildings to be built, because in the case of a building like Petronas in Kuala Lumpur, when that started, Who knew where Kuala Lumpur was? Who knew what Petronas was? Nobody. They researched it. They found out that there's an oil company. They researched where it was, and it became a moniker for the country and a landmark and an icon for that country. Another reason now is so national identity. Another reason now is the development of the tower itself. Still doesn't really make economic sense in almost any part of the world today if it's by itself. It's one of the reasons why in Chicago, when Calatrava did the spire at 2,000 feet, it never got built. Even though the foundation got built, it didn't make sense to the developer to go ahead because he was going to lose money on the construction of that building. It couldn't be overcome by the sales of the units that were in that building. It was too expensive for that. And unless you're a country or a multi-billionaire, you can't really afford to do it. So it stopped. And so developers and countries have now learned that they need to control the space around the tower that they're going to build in order to make their money on, not on the tower, but on the surrounding context to the tower. And so in these 30, 40, and 50-story buildings is where they make their money. And that's now a pretty well-known fact. And that's why that is the tenet for every building in China that is a super tall building. They always show the tower as part of a larger project where the developer can come in and make his money on the site, but they create an icon for the city itself. The two other interesting aspects about the tower here is the location of balconies in the quiet zones for the facades near the core. And you can see them here randomly placed on the three facades, tucking in and giving visual activity to the exterior wall. And sometimes they're spaced 4 stories apart, sometimes they're every floor, and sometimes they're 2 stories apart. It's an element of design that is meant to be abstract and somewhat random and purposeful to the composition of the tower itself. Near the mid to top portion of the tower, you see what is a disc, and that disc was initially designed as a request, a late request of the client. Can we put a helipad on the top of the building? Well, because the top of the building goes to a point, the answer was no, but we can try to put it on the side of the building. So we put a disc that would hold a helicopter pad, and that became part of the design of the tower. And we'll get into that a little bit later here. These are just views. The other component of super tall buildings, and the taller you go, the more the tower should have a mixture of uses, not just one use. Don't just make it an office building, period. Or don't make it just hotels, but have hotels, residential, office, and special uses, and usually an observation deck as well. You need to diversify the uses, and that also helps to diversify the risk from any developer that's doing a super tall. At the base of these buildings, they're quite large, but in this particular design, and also in the case of Burj Khalifa, where we used pavilions for the entry, this building we use a shell structure that brings the facade out and increases the size of the lobbies for entry points for hotel, residential, and office. And it also shields the wind that might be moving down the tower from interacting with people entering and leaving the building itself. So it has a number of uses, but one of the uses that we discovered on this particular building late in the game was, I want to get to a particular slide here, where the facades being concave in nature, we discovered that the sun orientation on those buildings was beginning to focus on the canopy of the the south canopy of the building itself. And rather than change the design, we thought this is a great opportunity to use the heat from that focused light source. So we put photovoltaics, we put solar collectors on the roof of that piece, so that we can generate power from that to run the hot water systems for the hotels and other aspects of transferring heat into power for the building itself. The facade, we originally designed as a smooth, slick skin, but as you know, right, roughly around 2010, when Burj Khalifa opened up and we saw the pyrotechnics happening there, and that was just a one-time event. But what happened after that for the next 2 or 3 years was sound and light shows that became nightly and hourly, and featured very much in terms of the iconic aspect of the building. And we had studied earlier the idea of doing that at the spire only to actually potentially do shows and advertisements electronically from the top, but that went away, and then it has reemerged. We also have small little buildings around the tower itself that are entry points to the ballrooms for the tower. And these are diagrams that are in our book that we are going to publish in a couple weeks, just to give an example of some of the content in this book. The lobbies are very evocative, both forms within the lobbies themselves and multi-purpose, because in several of these, the lobbies are on the second level, or there are 2 levels to the lobby for the double elevator systems that we employ for this building. And at the typical floors in the residential and in the hotel, we try to capture the character of the site and, you know, the surrounding context. In this case, the Red Sea is directly adjacent to the building, and and of course everything in Saudi Arabia starts out as desert, basically. So the forms of the sand building up is ever present in the character of Saudi Arabia's geology. And then I already told you the story about this as a helicopter landing pad, but when we started talking to, and the client loved it, so that when we started talking to helicopter people, flyers, you know, pilots, they said, no way we can fly a helicopter on that. It's too close to the building and it's too susceptible for risk. And so because our client liked it, loved it, he wanted to keep it, we said we can make this into the observation deck. So that's what it became. And then as we were designing it and talking to contractors about building the building, they said they really liked the idea of this platform up at 600 meters that they could utilize for staging the construction of the spire itself. So that became an additional advantage to this piece sticking out of the building itself. And it actually helped the possibility of getting the building built up to its 1 kilometer plus height. Another image of it. These are studies that our wind tunnel test analysis show how vortex action is on the building at any one point. We did the wind turbines, we did the wind tunnel tests in a number of ways. And this just shows what the effect of smoke moving through on a still life shows, but on these tests. But these tests are invaluable, and they should be done at the first idea. Once the first idea is developed, we should be doing wind tunnel tests at the very beginning stages to make sure and to verify that, at least from a wind perspective, there are no inherent problems in the design. You have to remember that these super tall buildings, many of them start, but very few of them finish. I mean, many of them start in the design process, but it's so difficult to get through the entire process and so expensive to do these super tall buildings that many of them fall by the wayside and don't go beyond the initial phases. This one is is also hampered by economic issues and other issues, but here this building started in 2013 with the foundation systems being built complete. It took over a year to do the foundations for this building. They go down some 300 feet or more in some areas, and a very expensive process. What you see in the photo on the left, upper left, is some of the rebar in the pad that's on top of the foundation, the 4-meter deep pad that then transfers the load more evenly to the caissons that are forming the foundation. But this building is up to about 70 stories, and then for a series of reasons, it stopped construction. So last I heard, which was about a year and a half ago, I think it was in November when I was in Saudi Arabia, roughly a year and a half ago, that the discussion was going to be that they were going to start construction in the first quarter of 2020. And you know what happened in 2020? The pandemic. The pandemic was started, and the tower never got past that point. So it's still sitting there, very much like you see in the photograph today, ready to go, but everything stopped. So you can see in the diagram, in the photograph on the model, where the building is up to that point, about 25% of the height of the building, 20 to 25%. So we hope it gets going. We've been told it's going to happen. It's just a matter of time and circumstances. It is a mixed use for office, hotel, residential, and 2 observation decks at the top of the building. And there is the top iconic photograph of what could be looming over the clouds in the distance. And as part of icons, I put this into this chapter because it's, into the show here because Central Park Tower is our first completed super tall building at Adrian Smith plus Gordon Gill. The structural engineer was WSP, the mechanical engineer was AFK Group, and this building is now 1,550 feet tall, which is 472 meters tall. We had originally designed it for a spire. I wanted the spire to be there, and I wanted it to be taller than the Freedom Tower, but it got nixed because our client Excel said, we don't want to ruffle feathers, and so we think that it's best if we just keep it at the 1,550. So the tower, the spire, dropped out of contention for that particular building and reason. But the building itself is is a figure point looking up Broadway, which is that view. But it didn't always start with that shape. It started as a tower that was sculptural in nature, and that was stepping up from the Broadway street and going towards the east and creating a strong silhouette looking at it from the east and or from the north and the south and from Central Park Tower. But events occurred after this design, such as the Bob Stern building in the foreground between the tower and Central Park, that made us reanalyze the architecture of it and the placement of the tower itself. And part of the placement has to do with the location of the Stern Tower to its north. And part of the solution for capturing as much as we can of the Central Park views was to cantilever over a portion of the tower over the Student League Club building, the 5-story building that's adjacent to it on the east side. And here you see the image of the cantilevered elements of the tower. Cantilevers out 30 feet to create 30 feet more of vista to Central Park, not blocked by the Stern building to the north. Another feature to this building, or factor to this building, it was designed with a lot of integration of wind turbine, wind studies for the tower. It's a very thin tower, and we were concerned about the vortex action on the tower because it's mostly residential. And we fine-tuned the building through numerous wind tunnel tests to size the notches of the corners of the building to where the wind effect was the greatest and where the wind conditions could be modified to mitigate the vortex actions of the building. So this building was fine-tuned in that regard. And it creates a silhouette on the skyline that's much like the stepped silhouette of many of the Manhattan buildings of an early era. But there's another unique aspect to this building, which is that most of the units within this building have that Central Park view, and they have another view which is very impressive, which is the view to the south to the Empire State Building and beyond. So the design of this building is also expressing the structural components of the building with the shear walls as blades coming out to inform the architecture on the outside, and also the cantilevers being expressed as cantilevered slabs and cantilevered elements that are grabbed by the mechanical floors as they go up the building. We also wanted to identify the central core of the occupied space with a facade that was vertical and that would shimmer in the sunlight and catch the horizontal lights from the early morning and the late afternoon suns. And so we came up with a polished element that sticks out beyond the glass face. And at one time it was sticking out quite sizably. And one of the research elements that impacted the building design here was innovative and new. It was looking at the facade itself for winter conditions, not just summer conditions, but winter conditions, and what would happen in driving snow. And we went through a whole series of shapes and iterations of the configuration of the the tube or the piece that projects out. And we did tests of it, not only wind tests of the detail, but also tests of how snow would drive and pile onto the fins and get gathered on the fins, and what size was appropriate for this without having the snow pile, freeze, and then being heated up later from the building and fall and in large chunks. We didn't want that, and the client certainly didn't want that. So the study was how to achieve a texture to the facade and would give brilliance to the facade with low sunlights, and still not create problems of snow buildup and potential hazard from falling. And so the study was done. That was an extensive study that was done for the facade to assure ourselves that the buildup of snow would be minimal, and that not come down in big chunks that could harm people or buildings. And the design of this building, from beginning, we knew that we would have to have a tuned mass damper at the top of the building. So we accommodated that in the very top of the tower, and now the top of the tower being lit up will become the sort of beacon for this tower at night. So what was next? We came up with an idea of integrating natural ecologies into the tower itself. This has been done with Ken Yang earlier in his, in the period of architecture, where he would integrate gardens into his towers, and they were in the 30, 40, maybe 50-story range, but nothing taller. Here we came up with an idea for competition in Suzhou, which is called our Biophilic Tower, and we didn't win the competition. I think Gensler won the competition ultimately on the site, but the jury liked the idea. They were just not thinking that they could do it at this stage. And the Biophilic Tower basically is the introduction of elements that would comfort the occupier. And one of those elements was the fractal pattern. That research says that fractal patterns of nature are calming to the human, and they're comforting to physical and mental health of occupants. And so we laced this exterior with several different scales of fractal pattern to form an image for the Biophilic Tower. We also brought that, and you can see the fractal patterns on the left screen there by nature. Some are leaf forms, some are dried water beds, cracking mud surfaces create fractal patterns, believe it or not. And then, so you see our model here on the right, and what's on the left lower is the inside of the model showing the fractal patterns. And if this were a green image, it would be covered in greenery. But the other thing we did here was we felt that every person, every floor should have access to an outside terrace that would have growth and planting in it. And so we wrapped the building with cuts on every floor that created a spiraling effect to the tower. And sometimes we clad it with the outside edge. Sometimes we open it up to the inner smaller level fractal pattern, and sometimes we open it up all the way to give a variance for the tower and to be less systematic. And there you see the impact of it from a couple of floors where you can see the fractal pattern through the typical floors. And there you can see more of the nature of the pulling away of certain elements of the facade to expose and create natural air movement through that spiraling element of the tower that gives terraces to the unit itself. And there are the image of what could be terraces at the terraces themselves, which are gently splaying up through the tower. Now I'd like to talk about Megatall. And for me, Megatall is not just another layer of height, but it has to do with the connectivity of towers and the ability of towers to have wind movement moving through the tower itself. And we weren't thinking of Megatall as a distinctive character when we designed this building, but it became the idea of Megatall once we explored the idea of 3 towers being interconnected at the base and bridged together or stitched together at different points of the building to strengthen the building to act as one. And so I wanted to show this tower to illustrate that what I think could be the next big move in terms of creating taller and taller buildings. This tower itself was tied with a base as well, and it was spanning over what was at the time we designed it a T-shaped canal system in Dubai, and the water would flow underneath adjacent to these 3 towers, but underneath the central point of the tower. And we thought this would be a great place to have events occur in the water with seating that could float out in the river or be docked at the sides of the river and then be moved into close off the 3 arches of the building that you see forming the base, so that at night there could be events down there. And I'll show you a little more of that later. The bridge design itself was challenging. We initially thought this could be a cable suspended structure and be cable braced from the bottom. Through our investigation and through the investigation of our engineers, Halverson in this case, it turned out that the strut system from the bottom was going to be more effective than cables, but the cables can still work at the top to assist in the gravity loads of the tower. And the engineering discussion was well advanced when this tower also stopped in 2008. These are a couple of images of the tower looking down through the 3 towers and the opening that's in the center of the bridge element. And there would be a 4th tower that emerges from this, which was a tower of light that could come up through the openings in these towers and create a special event. And then here's the base of the building where we move these seating areas into underneath the tower and attempt to do hologram type of performance events within the space underneath the triangular open air space. These were some early elements of that study. Here are some more that we looked at. And there was a platform that would come up, a stage that would come up through the middle of this space through the water. It would be underwater, and then it would come up and be above grade. And of course, the wind tunnel tests were done on this, and we were warned by the wind tunnel RWDI in this case that each of these 3 tower components would need to have their tops opened up so that there was the ability to wind to move through them. And So this was this first part in the step to redesign the top of the building, and we looked at notches on the sides of the building that you could see on this drawing. We looked at various configurations of and geometries that the facade might take as an experience to sort of diffuse the surfaces of the building as it got up towards the top, and how it would affect the body of the building. And this building was always conceived as a double wall building form. So you can see the double walls in there. And sometimes this skin we thought could be open or partially open and closed in other parts. And so you see the texture could change depending on where it is in the building itself. And those could be, those spaces could be utilized as balconies or solariums if they were closed off in the tower. We also concurrently looked at designs, and this was many different versions of the design and the skin. And we also concurrently looked at a simpler move of fins, glass fins that could be colored. And they could be colored glass that would actually, from the inside, you wouldn't really notice them because you're looking straight out through them, but from the outside, they could create very interesting colors in the facade as they layer one against the other. And then these are just some structural diagrams that were done that I wasn't going to focus on because I know that engineers are going to be in the second stage of the Skyscraper Museum program, so I won't go through much of this. And then shortly after the crash of 2008, we thought, let's do some research on Mile High. We had some additional people around. We didn't know when those projects were going to start back up. So we started looking at Mile High and could we actually build a Mile High. We started talking to Samsung about Mile High structural systems, and we came up with some step systems. And in the diagram there, the photograph, you see 1 kilometer tower and a Mile High tower next to it. Again, this was based on a much stronger connection between the 3 leaves of the tower, both from the point of view of those bridges that you see in the diagram and from the surrounding floors would be embraced with a grillage that would be a circular grillage that would help to tie the 3 leaves together as a single form, but yet let air movement through them so that you're not blocking the air from moving through the tower. And the center point would be the elevator systems that would be shuttle systems to sky lobbies that would then feed local zones for the 3 components of the tower. And then in another version of that, which we studied for a client who thought maybe this could go into Mecca, that we did a slick version of what you just saw in terms of a Mile High as an idea to whet the appetites of people. So far, it hasn't gone anywhere, but it could still be out there somehow. And inside that cavity, come back to wind turbines and the power of wind generation that could happen at a building like this. And it could be a very interesting space to view up and down in from the platforms as well. So that's where we are there. But I wanted to talk a little bit about something that popped up after those studies, which was developed by ESD, our mechanical engineer on the Jeddah Tower. And we started talking about at what point in height does it become uncomfortable for people to be? And they said they had just done a study about height versus oxygen content. They also looked at height versus temperature. Of course, every 100 meters or so, you reduce your temperature by a centigrade or so. That's gets into how you utilize cool temperatures to help air condition your space by drawing from the top floors and bringing that air down. But through oxygen and partial oxygen pressures, we get to a very basic diagram that shows on the vertical the oxygen in the atmosphere, and shows on the horizontal the altitude in meters. And in the yellow box that's in the middle there, we're looking at a zone between 900 meters up to around 15 or 1600 meters, which becomes the mile high, and how the oxygen level is at those heights. And at 900 or 1000 meters, it looks like it is in a zone that's just below the minimum required for normal function of a human. And at a mile high, it's approaching the limits of physical activity at someplace in between. So, you know, there's the issue of oxygen content to bear in mind. And of course, if you're in Denver, you're at a mile high, but you get used to that oxygen content. Your body gets used to it. But in a tower, is it going to get used to it? Because you're going up and down, and you're going from basically the green on that diagram to the red in that diagram. And how does it affect human occupancy of a building if you're, say, above 600 meters? So is that a cap that we should be thinking about in terms of human functioning in towers? Is that a cap to how high we can go? Or are there other limiting factors that we don't know of yet? We know how it reacts in 600 meters high, but there hasn't been any space that's occupiable basically much above 600 meters in the world yet. So it's an unknown. And when you go to the world's tallest building or the world's tallest occupied space, these issues are unknown. We don't know what we don't know. And these are always experimental buildings when you go to world's tallest buildings. And so mistakes are easy to make along the way. That's a warning. Anyway, that is the end of my formal discussion. And I think that we have some time, perhaps, I don't know, Carol, for questions.
Thank you so much for such an incredibly rich array of information. You really took us through every scale of the building. It's clear that you've got a 500-page book coming out in a week or so, because we tried to get kind of every aspect of that into the many dimensions of these super and megatalls. We are really over our time, but I am going to ask you to maybe summarize in a couple of questions. I know a lot of people have already been on their screens all day long, and I think we need probably another 5 or 6 hours in order to kind of draw out of you all of the kind of cross currents and themes. So you kind of surprised us at the end by saying maybe it's maybe it's the frailty of the human body that is going to be to cap how high we can go. And you certainly suggested that there is no limit to the architectural imagination. There doesn't seem to be a limit to the engineering solutions that would allow us to go super tall and mega tall. But there is this most persistent question, and it has appeared in the chat over the course of your talk. We know perhaps how high we can go, but how high should we go? And I think that you tried to illustrate for us the reasoning that you bring to that question by applying these principles of sustainability and the trade-offs and the ingenious trade-offs in thermal patterns that allow you to adapt the physics of energy into a solution for comfort in buildings. I think that that there's still a lot of people suspicious about those ideas and whether they should be applied in a world of increasing climate change, of this kind of cycle of maybe artificiality that may exist in our natural world. And I know that you have also, in the really deep research that you undertake in your firm and with Gordon Gill, to ask questions about what's the most responsible way to live on the land. And I know that in Chicago you've done studies just on your own dime, in effect, not commissioned studies, but to try to understand how to conserve energy, how the city could conserve energy by using the grid more effectively. And I know that you've done recently studies about low-rise buildings and analyzing them and finding them more efficient. So can you answer in the kind of simplest summary, there's the persistent question about how high should we build?
Yes, I think we have done two major research projects on our own dime. One was to take a city like Chicago, like downtown Chicago, a dense, urban, compact environment, and to see what we can do with existing buildings and new buildings in that compact environment to meet the stated goals of the 2030 challenge, otherwise known as the Kyoto Treaty. And how do you get a city that's already built to meet a challenge, which means that you need to reduce your reliance on the grid by something like 80%. And believe it or not, part of that is the function of the building itself. Office buildings utilize about 4 times the amount of energy of residential buildings. So we found that in that compact environment, which was almost like 99% office building, if we were to be able to rework those buildings so that 50% of those buildings became residential in nature versus office building in nature, that would significantly reduce the amount of power output needed to run the loop. Just that one thing. And how do you do that? So the idea was to make the loop livable for families, not just singles or doubles, but to really make it rich and vibrant and livable for families. And an important ingredient of that is to bring educational facilities for children and young teens up through college level into that environment so that they can walk from their home to their school. And if they can do that, and you can have 50% of it as residential, you can take the elevator down to your office floor, or you can walk across the loop from your residence to any place that you're working in the loop. So it becomes a live-work component. You know, the city becomes a live-work environment, and you can almost eliminate the number of cars that you need in terms of people commuting from outside that space into that space if you make it a live-work environment. So that's one thing to consider for all of the cities that are already built. How do you make them more conducive to climate change and to what we like to prefer calling it is carbon neutral environments, so that we reduce the amount of carbon that's being put out into the atmosphere, which it then begins to pollute the atmosphere in a number of ways that are negative. And so that pollution the carbon is generated by fossil fuels, obviously, but it's also generated by peak loads and all sorts of other issues that come to the forefront. And we think and we know that if we can generate power at the site of the building, not 20 miles away or not at a power plant, but at the site of the building, we're saving 70% of that energy that we would otherwise waste in transmission or in the heat from the transformation of one power source to another. 70%. That's a significant thing. So it's not about PV farms out in the distance. It's not about wind farms out in the distance that have to be transporting that power to the central city. It's about creating the power within the city. It's about double wall environments, about using the geothermal temperatures from the soil to mitigate the differential temperatures of the building, et cetera, et cetera. So it's a very complex discussion. It's not just about height. But about height, we studied 10 different typologies of building, from 200-story towers to a building on a residential unit on a quarter-acre site, and everything in between, bungalows and three-story walk-ups and 10-story buildings, 20-story buildings, 50, 70, and on up. And we did a very extensive energy calculation on the utilization of each of those types. The super tall buildings, the 200-story buildings, were the greatest offenders of the energy usage, because not necessarily because they are tall, but because they have to be engineered to be tall. And the efficiency of them is lower. Normally, a building in the Burj Khalifa range is about 65 to 70% efficient. You're utilizing corridor spaces to get to all those units. You're utilizing lots of shaft space that's going up to get to the top of that building in segments. You're using structure at the base of the building that's very powerful structure to support the buildings above it. That's much more so than if you were to take the top 40 stories of a building and put it down on grade. You can take the top 40 stories of a building down grade and you can put it on top of that building, and with some manipulation, it's about the same building. But the height of a building is typically causing these systems to be more inefficient. Now, an interesting thing about the Central Park Tower project is because it's small in footprint and it's a point-like tower by its nature, the structure is a higher percentage than if it were a shorter building, for sure. But there are only 2, 3, maybe 4 units at most on these floor plates. And so the corridors are almost non-existent. So these are much more efficient buildings if they're point-like structures than if they're broad towers like Burj Khalifa or Kingdom Tower. So that helps mitigate the energy issues that you've just talked about. So that's one of the considerations that should be brought into the picture. The other aspect of all this is, in that study of tall to short and in between, the effect is that basically a 3-story walk-up is the most efficient typology. 3 to 5 stories is the most efficient typology in Zone 5, which includes Chicago and New York. Weather-wise, it's specific to that zone. It doesn't get into the Saudi Arabian climates. But this is a book that we did on residency is the book that we call. It's named Residency, and it has all of the calculations for every typology in there and why. And then when you take the fact in consideration that a tall tower has 2,000 units and is only occupying, say, 4 or 5 acres, whereas a single family on a quarter-acre block is occupying 600 acres. You know, it has infrastructure that has to reach out to it in both road systems, sewer systems, power systems, et cetera. Those also add to the carbon neutral or carbon usage of these densities. So the 3-story to 5-story walk up tends to be the sweet spot between those two. I.e. Europe.
Well, that may seem to be an ironic place to conclude the discussion for the Skyscraper Museum, and especially for the topic for this evening. But I think it pretty clearly underscores for the people who stayed with us for an hour and a half tonight of Adrian Smith, that his mind ranges both wide and tall. Can't say high. That, I guess that would be that would have a double meaning. But it's clear that he brings his rational analysis as well as his creativity to all of these questions. And so I guess people will have to buy a 2-volume set, one on Supertall, Megatall, and then the other one on the low-rise analysis, and take both sides of the coin for thinking about a sustainable urban future. So thank you, Adrian, tonight for a very rich and provocative talk.
Thank you for inviting me.
Okay.
Appreciate it.
Bye, everybody. Come back next week for Bill Baker when the Engineers series launches, and we talk about the 21st century typology, including some of the of Adrian's first buildings in China. So join us then, and we'll have even more hours of indulging in our love of Supertalls. So see you next week, everybody. Bye.
Bye-bye.
Hello, everybody. 6 o'clock, and welcome to the 6th of our Worldview Designing Global Supertalls. This is the last of the first half of the series that features architects who are the design principals in their firms of some of the world's tallest buildings, all Supertalls that are featured in our Supertall 2020 exhibition at the museum, still to open officially to the public, but we hope maybe later this spring we'll have the opportunity to turn the lights on. I'm in the gallery now. Among the featured towers that I will show you in a moment in this slide. But tonight we have as certainly the if last, but absolutely not the least, of the architects who have designed Supertalls in the 20th century, 21st century, and at the end of the 20th century, Adrian Smith. Adrian Smith, who co-founded with Gordon Gill, Adrian Smith and Gordon Gill Architecture in 2006, having spent a little more than, I think, 30 years at Skidmore, Owings and Merrill, where he designed many a tower, many a skyscraper, and many other kinds of buildings. But as you see on our screen here, advertising his and describing his lecture for tonight, the Burj Khalifa, when he was at SOM, led that design team, and which is the current world's tallest tower ever since 2010, and the design of a building now under construction, but stalled at the moment, that will become, if finished, the world's next tallest tower, and it's one of the ones he'll talk about in his lecture tonight. The topic of which is Supertall, Megatall, how high can we go? It's a serious subject, and he is certainly the person to be able to speak to those design issues, because as I calculated in the first sentence of this of our our web page on Adrian's talk, that he's the architect of more than 4,500 vertical meters worth of Supertalls. That's more, well, I guess it's nearly 2.8 miles if you pile them one atop each other of skyscrapers. He is the king of the Supertall. There are 8 buildings in our exhibition that I'll show you in a slide in a moment that are his design projects. And let me go on to show you some of those additional slides and to reiterate that worldview. Designing Global Supertalls is a series that looks first at architecture, then at engineering and constructability. I'll show you the schedule in a moment, but beginning next week, we focus on a lineup of engineers, beginning with Bill Baker, who will talk in a fairly historical way about the development of the 21st typology of the Supertall. So please join us for that part of the series. The buildings that, as you know, we've featured in the exhibition and in this lecture series, you see in succession are featured buildings, all of which explore innovations in form, as well as, of course, of engineering. And you see the Burj Khalifa in this lineup, as well as another design by Adrian for the Chengdu Greenland Tower. The last of the towers there is not his, but the Lakta Center in St. Petersburg that Ahmed Abdelrazak will talk about at the end of our series. So, the idea was to focus in depth at these series of featured towers in the exhibition so that we could really explore in all of their dimensions of design and development those towers as well as their broader context. Adrian is the architect for 8 of the towers in our exhibition. The criteria for the Skyscraper Museum Supertall is 380 meters or taller. And you see here from the lineup where we compare in the show in a big graphic mural, the buildings scaled to each other along with their plans representing them. You can see in chronological order the bookends of Adrian's first work in China, the Jin Mao Tower, that he was the lead designer on when he was at Skidmore, Owings and Merrill. And then 7 other towers, including the second to the last that he'll talk about tonight here in New York, the Central Park Tower. And then the design that you can see of the Jeddah Tower, which is the other one that he'll feature on, of buildings that have been carried through their design development drawings. The other projects I won't talk about here, but you can learn more about them on our website. But I want to mention and preview that Adrian has titillated us with the idea of how tall can we go with Supertall and Megatall. But as he'll make clear from his slides and his presentation, it's the idea that sustainability and height are not antithetical to one another that he's going to explore in his talk. So as I just show you in, I guess, a last slide, the title of his talk, I'm going to ask Adrian to turn on his camera and share his screen so that we see him. And then I think he'll disappear so that we get the full panoramic wide view, world view presentation. So, so here is Adrian Smith, the king of the Supertalls.